तो भी खींच लीजिए ना बीच बीच में।
Good morning, sir. Sir, good morning.
Good morning. Good morning. How are you?
Yeah, fine, sir. Okay.
Okay, I'm just trying to see whether that sharing is possible.
Okay, sir. Yeah, yes, sir. Good morning to everybody, and our respected resource person, Engineer Biswajit Chakravorty, Scientist J, and Head Center for Flood Management Studies, National Institute of Hydrology, Roorkee. So today, we have two sessions. On the first one will be on this evaluation of river bank erosion using river flow model, and second it is urban flood modeling. These two issues are related to both this flood and erosion, and one of the most relevant issues related to the erosion. So here, because in our country we have the issues of flood in urban areas, like cities, like some cities of the country, like Kerala, Uttarakhand, in metropolitan cities like Delhi, Mumbai, Kolkata, Guwahati, are facing this problem of urban flood. So, because of various reasons, the urban flood is also increasing day by day. So, we need proper methodology, proper management approach for its management. So, today we are fortunate that we have an eminent personality deliver on this subject. So I welcome you, sir, to deliver on this topic. So thank you, sir. Please.
Good morning to all of you. First of all, let me thank the course organizer as well as Madam Victoria for giving me the opportunity to participate in the training program. And I thank all the participants who have joined for this training. So let me briefly introduce myself. I am Biswajit Chakravorty, working as scientist with the National Institute of Hydrology located at Patna. So today I shall be delivering in fact two lectures. First one will be on performance evaluation study of anti-erosion work using a river flow model. So here we'll try to understand the step-by-step procedure with the help of an example that when we should be alert that we need to concentrate on the on anti-erosion structure. So let me try to share my screen and then let me start my presentation in detail.
An announcement, sir. We are having the live YouTube during your presentation also. Those who are not able to join in this link, they can directly join in. They can directly connect to the YouTube so that they can hear sir's lecture. And I request the participants to give their questions at the chat box so that after the completion of the lecture, we will have a discussion on the questions put by the participants. So kindly put your questions at the chat box.
Okay, thank you, ma'am. Uh, so is the screen visible and am I audible?
Yes, sir.
Okay. So during next 2 hours or 2 hours, maybe I expect that I will finish in 2 hours. So we shall be talking about two topics. Number one is performance evaluation of anti-erosion work, performance evaluation study of anti-erosion work using river flow model, and we'll be taking a case study. So, as far as river shifting is concerned, we are all aware. And when river shifts, then there is a fear amongst the people living in the floodplain because these threaten embankment and village. So, in this presentation, I shall try to justify the requirement of anti-erosion work, whether it is at all required. So, here I shall be taking the help of remote sensing analysis. Then I will switch over to if that anti-erosion work is necessary, then we shall be dealing with the hydrological data analysis. Here we shall be dealing with flood frequency analysis, wherein we will compute this flood for different return period. We'll also try to collect the data for the discharge as well as the cross section available in the nearby site. So once we are through with the hydrological data analysis, we shall be switching over to hydraulic modeling, wherein we shall switch over to HECRAS. ECRAS means it's a hydrological engineering center, river analysis wing, and with the help of this software, we shall be computing the water surface profile as well as the velocity in the affected area. Then, so once we are done with the water surface profile as well as the velocity, we shall assess the appropriateness of design parameter as per the relevant Bureau of Indian Standard codes. Then we shall also try to understand the cost benefit of the project. And in the second part of my lecture, I shall be dealing with modeling of urban flooding and management. Here also, I shall be dealing with a case study. And as you heard, that urban flooding is a very serious phenomenon nowadays. Almost all the urban cities are, you will hear during the rainy season that they are flooded. You might have heard about the flood in Mumbai, flood in Chennai, also flooding in Patna. So I shall be giving you an overview of the flooding occurred in Mumbai, Chennai, as well as in Patna through a visual through YouTube. Then I shall switch over to my normal presentation, and also I shall try to simulate on screen that how suppose x quantum of rainfall is occurring, how the system is behaving, and if the quantity of rain is more than the quantity of outflow, then there will be flooding, and if there is flooding, then for how much duration we are going to suffer. So those kind of thing we are going to deal. And on the screen, you might be seeing that I have given my email ID as well as my contact details. So let me first deal with the performance evaluation study of anti-erosion work using river flow model. So it's a case study at Arjunpur and Umarpur villages in Buxar district of Bihar. So I shall be presenting this case study. So first of all, let me familiarize you with the location of these two villages. The study area is uh, near the Buxar Koilur Ganga embankment. It is located on the right bank of river Ganga. The river Ganga has touched the embankment. This is the background of the anti-erosion work. The river Ganga has touched the embankment near Arjunpur and Umarpur village, and therefore anti-erosion scheme was constructed during 2002. So the sites are located in Buxar district of Bihar. So this is the location. This is Bihar, and this is where we are focusing. And this is Ganga River flowing from the west to east. Here is a village. It is named as Arjunpur, and here there is a village called Umarpur. These two villages are severely affected during flood. So first of all, see this case study, why I am presenting, this will give you an insight of the step-by-step procedure to be followed. First of all, the remote sensing study, which will give you whether the village is in danger, whether the embankment constructed is in danger, whether there is a likelihood of the embankment being breached and the flood water enters into the village. So that is what has happened in these two villages in the past. So first, let us try to know why these anti-erosion structures were necessary. So this is the anti-erosion work that was constructed in 2002 for a chain length of 30 chains. Each chain is 30 meter in length. So it is 30 chain means 900 meter. This is 900 meter. And similarly, in Umarpur, there is anti-erosion work that has been constructed. So this is about what has been done, and this is the means blow up of the location map of the study area. Now the project objectives. Now preparation of map showing the river bank line and embankment condition before and after the project. Am I audible? Hello?
Yes, sir, you're audible.
Yes, sir, you are audible, sir.
Okay. Then let me proceed further, because in net connectivity sometimes we are not sure whether my voice is reaching you or not. That is why I am very much concerned. So preparation of map showing river bank line and embankment condition before and after the project. We were asked to find out whether the anti-erosion work was necessary. Number two, if anti-erosion structure was necessary, so, and it has been constructed, so what is its fate once it was constructed? So evaluation of durability of anti-erosion work, then evaluation of design criteria adopted in the construction, then cost benefit of the project. So since the first part of the study was dealing with the remote sensing data analysis, so we had to get the remote sensing data. So we use IRS 1C, 1D. Along with that, we also used PAN data so that we get details of the embankment and other details. At the same time, we also had the Cartosat data having a resolution of 2.5 meter. PAN data is 5.6 meter resolution. So this is about the satellite data that we have used. Along with that, we have used hydrological data from CWC, annual from the annual maximum GD site at Buxar, river cross section from Water Resources Department, Government of Bihar, as well as from CWC. Then socio-economic survey, we went to these two villages to ask the inhabitants of these villages whether that has got the anti-erosion structure has benefited them. So methodology, preparation of river bank line and embankment maps. So here we have analyzed the temporal satellite data. It consists of georeferencing of images of various dates, delineation of as you saw earlier that these two villages are located on the right bank of the river Ganga. Delineation of right bank of river Ganga and delineation of embankment. Satellite images are also analyzed for assessment of any damages or flooding in the nearby area. So this is the first thing we have done. So now let us try to see the details. So the base information we got from Survey of India Toposhit 1971, and we took the satellite image of 2007, and we could find that there was in fact there was a shifting of the river towards the bank by a magnitude of 140 meters in Arjunpur and almost a kilometer in Umarpur. So this is we have compared the 1971 Survey of India topo sheet and satellite data of 2007. So now we have tried to draw the bank line. So in different years with time. So here what you find, this is the legend. So here you find that 9th February 2001. I said that the embankment was constructed in 2001, 2001 and 2002, and the river threatened the embankment during 2001. So we analyzed the satellite image of 2001, and we could find that the bank line has touched the embankment, so the village was in danger. So let us see what happens to the other village, Umarpur. So here we find that from the satellite image of 9th February 2001 that the bank line shows that the embankment has breached almost half a kilometer, and the water entered inside the village. So once the water entered into the village, villagers tried to go away from the village and find their livelihood somewhere else. So there was a shifting of the inhabitants of the village from Umarpur as well as from Arjunpur. So second thing what we did was evaluation of durability. So here we have studied the river bank line and embankment condition to assess the effectiveness of the structure to sustain the annual peak flood. So we had the data prior to the construction, during the construction, and after the construction. Let us try to see before the construction, during the construction, and as well as after the construction of the anti-erosion work. What is the fate of the bank line, etc. So here, this is pre-construction scenario, and this is a satellite image of 9th February 2001. So here we find that river bank line has almost touched the embankment, so the village is threatened. So some work is going on. The people have started some work. So next slide, let us see. So this is during the construction. You see, during the construction, you find that some of the things have been cleared. This is shown in white patches, cleared, and some of the boulders have been laid. So this is clearly seen. So we can say here that yes, work was going on this date, 7th August 2002. So it was completed in 2002, and let us see further. 21st October 2004. So here what we find that the river has gone away from the embankment. So and there is also wet soil. That is this is in October. Wherever we constructed the embankment, you find the wet soil here, and this is the river. And at the same time, the river is away from the embankment. Now let us see further. So this is 26th May 2007, post-construction, pre-monsoon scenario. See, this because of the anti-erosion work, this portion has been shielded, and I will show you that there is lot of vegetation that has come, and even people are growing some oilseed crop, as well as some pulses. So this is pre-monsoon scenario, and this is post-monsoon scenario. Post-monsoon scenario also we find that the village is protected. Now let us see what happened to the other village. So here this is pre-construction scenario. During the construction, you can clearly see the anti-erosion work that has come. Clearly it is, you can demarcate. This is in 2002. So this is post-construction, this is pre-monsoon, and this is post-monsoon. You can see clearly the anti-erosion work, and you see that the river has gone away from the embankment. Initially in 2001, it has cut the embankment and entered into the village. So we went to the field and tried to see what has happened. So these are the places where anti-erosion work was done. People are growing crop. Here you find that some arahar or some oilseed crop has been grown. This is the condition of the embankment. Somewhere you see well laid stones, but at some places you will find that this wire net is missing. At some places these are in good condition. Somewhere some maintenance work is required. So that is what we found during our field survey. So see here there is a lot of silt that has deposited, and there is a lot of pulses that has come in this area, and they are taking a good harvest from this area. Since these are fine silt deposited by Ganga river, so there is a lot of crack. I have put my pen here just to show you that how much crack has developed, and people are even cultivating. You see below this there is anti-erosion structure, but here and now they are cultivating. Now let us go back. Next is evaluation of design criteria. Project authorities or the Water Resources Department, Government of Bihar has already constructed the anti-erosion work with the background that this much flood level may come, this much thickness of apron is required, weight of the stone should be this much. So we had to verify those things. In while executing a project, you have to do this thing afresh. Means as if only input is from remote sensing analysis, if you find that there is a threat of the embankment or the village is in danger, then anti-erosion work is necessary. And number two, what are the design parameters? So here, what we have done is hydrological data analysis. Flood here we have done flood frequency analysis for estimation of flood of various return period and the return period of the annual floods occurring after the construction of the project. Then we had to compute the maximum flow velocity and maximum water level at the anti-erosion site corresponding to 25. See, I have written here 25 years return period. So guideline is available where they say that if you want to protect village or agricultural land, the return period should be 25 years. Then
I think our resource person has got some technical problem. So I'm sure he will be joining soon. There is some network issues out there. Meantime, we would like to request the participants about to say anything regarding about our training program, because they have been attending since yesterday. Okay, sir is on the line now.
Yeah, let me try to share again.
Yes, sir. Yes, sir.
These are the problems that occurs most often. Is the screen visible, or do I have to? Is the screen visible, ma'am?
Yes, sir. Yes, sir.
Okay, here we found that we could compute that 47,000 Qmac is the. Now, I was thinking that if I can show you the how to compute the this one, then it might be of some use to you. Um, Let me try to share the screen. Just a moment, let me. Is the Excel sheet, can you see the Excel sheet?
Yes, sir.
Okay, so let me give you because I thought that it will be better if I can show you with the Excel sheet how to compute the flood for various return period uh, using Gumbel and log Pearson type 3 distribution. So here, as you find, we have data set from means historical data set. This is from 1956 till 2005. Okay, so Gumbel distribution says that the discharge is to be computed by xt is equal to this uh, average plus frequency factor into a standard deviation. So here what we have done is we have calculated the average from this long series data. We have also calculated the standard deviation. These two things are required, and we have to compute the KT. So here you find that we we have also calculated this, and we have finally we have calculated the this frequency factor. Calculated the frequency factor, we could calculate the this is average, this value plus this standard deviation into frequency factor. So this is how we have computed the flood for various return distribution. So here we find that the 50-year return period is 4473 cubic. So similarly, from this long series data, we have calculated, these are the discharge data, we have found out the log, and then we computed what is the average, standard deviation, skewness, as well as kurtosis. This can be done by Excel, and then we have to calculate what are other parameters like W. Here it's W. Once we calculate W, we can calculate Z. So these are the formula, how to calculate Z, and then finally this frequency factor, this big formula. So once we click here, we know what are the parameters that has been used. So once we do this calculation, we can find out what is the flood, and this flood for various return period. This is in log, and this can be, say, anti-log of this will give the flood. So here we found that with the Gumbel distribution, the flood computed is lesser than the log Pearson type 3 distribution. So we adopted this log Pearson 3 type distribution discharge for the analysis. This is just an example that I have shown for one of the tributaries of Ganga River. So is it clear? Could I make things clear that how to calculate? Because this is because everybody knows how to use this Excel sheet, and if we put the formulas in Excel sheet, it is handy for us. We don't have to. We can do it on our own. Plot for various return period like 2 years, 5 years, 10, 15, 20, 25, whatsoever it is. Once we insert the formula, things are very easy. So let me go out of this window. And again, let me go. Share. Okay. So this is just an example that I have shown you. So once we are done with this, so then we apply Heck-RAS model to compute what is the water surface profile as well as the velocity profile. So we divide the flow length in different segments, and these are called cut lines. And this is the village Arjunpur, and this is the village Umarpur. So here we calculate the velocity profile, and here we find that maximum velocity is 2.88 meter per second. And then we also compute what is the water surface profile and find that the maximum level this can attain for a return period of 25 years flood for Umarpur as well as for Arjunpur. So once we know these two values, then we can go further. Checking of design parameters with BIS code. So we have to calculate weight of the stone. The weight of the stone W on horizontal bed is expressed as W is equal to this expression. See here, what I like to emphasize as is V is the mean velocity of water in meter per second. So until and unless we are able to calculate what is the flow velocity corresponding to 25 years or whatsoever is the return period that we adopt, so then it is V raised to the power 6. So this is very sensitive parameter. So we have to be very careful, and we have to calibrate HECRAS model with care. So here SS is the specific gravity of the stone. This is 2.655, and W is the weight of the stone. Now there is another problem. The weight of the stone estimated is for horizontal bed. Estimated for horizontal bed would not be sufficient for the same velocity on the sloping bank, because only component of self weight normal to the slope act as a stabilizing force. So we have to make a correction with some factor. This is expressed as this, whether theta is angle of bank slope with horizontal. Here bank slope is horizontal is 2, vertical is 1, so theta is 26.56, and xi is the angle of repose of material, material of protection work. This is 30 degree. So K we find that it is 0.447. So weight of the stone should be 17.49, almost 18 kg. Then size. Size, likewise, this is the expression, and we compute the size 0.23 meter. Then thickness of protection layer, T is the thickness. So we substitute these values and find out what is the T, and it is seen that it is 0.25 meter. Now, these are the means this is where we had to make a check that whatsoever the project authorities after have constructed this anti-erosion structure, whether this fits to what we have got from hydraulic modeling and comparing it with the BIS code. So here we find that whatsoever means thickness or weight they have adopted, this is as per BIS standard. The design adopted for construction of anti-erosion work at Arjunpur and Umarpur site. So this is the design that they have adopted. So this is what we have calculated. As per the project detail, the stone boulder of size 225 mm to 300 mm, weighing 40 to 54 kg, they were put in crates of size 3 meter by 1.5 meter by 0.6 meter was used. Filter was also provided as per BIS code. The upstream and downstream end of the anti-erosion work have been provided with anchors. Therefore, the design is as per BIS code. So that is what we have verified, that whatever anti-erosion work was done, this is as per the BIS code. Now the question may arise, why we did all these exercises? What was the background? In fact, the project authorities, the government of Bihar, they wanted to protect some more areas downstream. So before giving a nod from Government of India, they wanted the existing structure, for the existing structure performance evaluation to be done. So that is where we were involved. So what we found that the design is as per BIS code. Now next part is, so this is about evaluation of design criteria, that we have checked that design criteria is okay. So next is cost benefit analysis. The project benefit have been assessed through prevention of flooding in the study area, through satellite imageries, and analysis of socio-economic data collected through field surveys. The cost of the project is considered as the actual cost of the construction, and the cost benefit analysis has been performed. So here what we have done, we have gone to the villages, we have interviewed the village people. You see permanent structure, this is a school building that has come. Earlier it was not there in 2001, people have fled this area. Now people are settled. You find that all the villagers are taking interest in answering our question. They have cattle, they have permanently settled. They have also expanded their agricultural activity. You find that they are engaging themselves with modern tools of agriculture. Here you see some children are playing, so they also have means harvest means thresher. So their lifestyle has also enhanced. They have pump houses. Also, they have here it is a tower, communication tower. So this is school. So initially in 2001, we saw the story that villagers are leaving the village. Now they are permanent settlers. So it has served its intended purpose. So here we can say that flood protection work in general may be considered as effective in protecting the BKG embankment. Means this is Baksa Koilior Ganga embankment. And for Arjunpur and Umarpur village. As per the hydrological analysis of annual peak at Baksar bridge, the design peak discharge need to be about around 48,000 cubic, whereas the adopted design discharge is according to the project as per the project proposal is around 43. So there is a gap. But nonetheless, we have checked the design parameters, height of the embankment, etc. Those are as per the BIS code, and that is as per the water surface profile that has been computed using HECRES. Design of revetments is as per relevant BIS guideline. Now, means we have done hydrological analysis, we have done hydraulic modeling, etc. But in the background, what is the means starting point? Starting point is we have collected remote sensing data, and we have tried to analyze whether river bank line is protected or not. So remote sensing data is a powerful tool to assess the efficiency and durability. Durability was also checked before the construction. We could analyze that anti-erosion structure was necessary. During the construction, we saw that yes, the construction is in progress, and after the construction, whether it has served the intended purpose. So we can also see the durability of the hydraulic structure for the flood occurred after their construction. It is also helpful in finding out the effect of construction of the structure in the upstream and downstream direction. So if there is any effect after the construction of this anti-erosion structure, either in the upstream, because once you put some hindrance in the river, so definitely you expect that means there is likelihood, maybe less because of the design that we have adopted, but there is likelihood that upstream or the downstream of the anti-erosion structure may be affected. So that is also possible to analyze using remote sensing data. It may also be used for locating new critical areas for anti-erosion measures where it is required. So this is the result. And now benefit, we have protected the agricultural line. We have also stopped the migration of people and the development of the village. So now they are permanent settlers and they are in prosperity. So now, yesterday there was some question from a participant that danger level. What is a danger level? So I could find out from the handbook for flood protection, anti-erosion and river training works. It is CWC 2012 at page 2. It is given. So it's a very informative, very simple information, but very informative. Danger level is defined as a level of the river. So this I just noted because these are relevant for the present study what we have conducted, as well as there was a question yesterday. So a level of the river depicting the stage of the river which, if crossed by flood waters, will start damaging the crop. So first criteria is if it damages the crop and property, crop and property, and will affect the daily life of population. So this is the danger level. This level is to be taken as minimum flood level, medium flood level, or zero point 0.3 meter below the plinth level of the residential areas. So they have also tried to pinpoint if the water level is below 0.3 meter of your plinth level, then it should be designated as the danger level. Residential areas and industrial complexes as fixed by the civil authorities, whichever is less. So this is the definition. Warning level is a flood level 0.6 meter to 1 meter below the danger level. So this is warning level. So this is danger level, this is warning level. Highest flood level are ever, this is ever recorded at the place. Very high flood, any flood which exceeds 1 in 100 years frequency, means here T is 100 year. Floodplain is the land adjoining the channel which is inundated only during floods. So this is what I like to convey. So here, should we take the questions now, or should I leave it for later? I think it will be better if I start the next lecture now, and maybe then we take in the end. Will it be okay?
Discussion may be held at the end, sir.
Okay, okay, sir. Thank you. So this, let me try to share the next screen. Just a moment, let me try to share the screen. So is the screen visible and am I audible?
Yes, sir.
Okay. Here the topic is modeling of urban flooding and management, and it's also a case study. So in an urbanized city, you find that although a lot of development has taken place, but during rainy days, you will find that there is a havoc. So before starting my presentation, I'll give you a background of the recent urban floods that happened in Mumbai in 2005, Chennai in 2015, Patna in 2019. So I will give you a background so that you can yourself visualize what is the gravity of the problem, how people suffer. Then it will be illustrated with some online video. Then I shall discuss some processes, then some components of storm water management model that we have used for managing or dealing with the urban flooding of Patna town. Uh, and this storm water management model that has been developed by United States EPA, Environmental Protection Agency. Then I will also try to show some simulation online, so that you can better appreciate how things are dealt with. Like in simulation, suppose X quantum of rainfall is occurring, how the total network of drainage system is behaving. Then if rainfall exceeds the capacity of the drainage, then whether there is overtopping of the drainage system, and if there is overtopping, then it is going to the nearby areas, causing inundation or waterlogging, causing miseries for the people living in the area. And this simulation will also give you a feel of suppose if we have a if there is a lot of rainfall, so for how much time we need to be in our house, or what are the protective measure that we need to take. So now, just to give you some background, this is modeling of urban a case study of Patna. So let me go back to 2005. Mumbai flood 26, 27 July 2005. So here you find that everybody means there is a lot of rain. People are with umbrella. These cars, car etc. This is underwater. People are knee deep in the knee deep water. People after their office hours, they are going back to their home. A rope has been tied pole to pole, and these inhabitants in the area, they are following the rope to go to the safer area. You see, bus is half flooded and people are on the rooftop of the bus. This is 26, 27 July 2005. So in the newspaper, I have the cutting of the newspaper of 2005. I have kept it. The headline was Mumbai sinks, India shivers. It was the caption in the Telegraph of 28th July 2005. Torrential rain plunged the financial capital into a black hole, jeopardizing all the modern day lifetimes that metropolis took for granted. The inhabitants of Mumbai, they never thought that they will have a miserable life like that, ever. The comfort they used to enjoy in their daily life, they took it for granted. Mumbai airport stayed closed, train services disrupted, many cancelled, even ATM of banks with Mumbai bases stopped functioning. Communication links were snapped, forcing thousands to sleep in their offices, stay stuck in cars or walk for miles. Even you might have heard that people inside the car, they were stuck in the car and there they could not survive. School children also marooned in school through the night. Most network of cell phones simply fell silent because of power failure. A handful commuters were lucky to reach their home after walking for 14 hours, walking on rail tracks and wading through chest deep water. Firemen tied ropes to lamp posts and a chain of people held into it to get through water. Many people died in the city. So that was the scenario in Mumbai. Now let us try to see in technical terms. See, this is the highest one-day rainfall over Santa Cruz in June 19. Means all are in June. One-day rain in June 19, and the maximum was 399 mm. One-day rain. Highest one-day rainfall over Santa Cruz in July. So this is June, this is July, 1974 to 2012. See, here you find that 944.2, highest one-day rainfall, July 2005. So this was the highest rainfall. From 1974 till 2012, you find that all values are lesser than, means even not even half, 351, 375. This is the figure in Santa Cruz. There are in other places it is 994 mm also. Somewhere it is said. So this is the highest ever rainfall that was recorded between 1974 till 2012. So this is in September. This is in August. See here 364. So 4 months we have tried to put all together. So highest one-day rain in August 1990. It occurred in 1997, 346.2 mm. In the month of September, highest rain was 318 mm. One-day rain. Now let us try to see in detail the rainfall that has occurred between 26 and 27. This is from IMD Santa Cruz. Very heavy downpour with intensity of 380 mm for 3 hours between 14:30 p.m. This is 14:30 p.m. to 17:30 p.m. So these 380 mm in 3 hours. That is more than 125 mm per hour. So this is very heavy rainfall. So this is between 8:30 on 26 till 8:30 on 27. This is 24-hour rainfall. This is more than 5 times the intensity of rain for which the drains were designed, and 2.5 times more than the intensity of the rain for which drains are currently being designed following their. This was subsequently more than the design capacity of the stormwater drainage system, and hence flooding was inevitable. Now you see this. How much was this rainfall? Here you find that this is 125 mm per hour. 3 hours rain was 380. So 1 hour duration in hours. You see, it is this has got a very high return period. This high rainfall. So drainage system is bound to spill out, and affect the nearby areas. Chennai Flood 2015. Very heavy rain associated with cyclonic activity resulted in catastrophic flooding in Chennai during 1943, 1978, 1985, 2002, 2005, 2015. So this is not in 1 year that Chennai flood has occurred. It has occurred in many years earlier. In 2005, a 100-year return period rainfall of 40 centimeter in a day caused heavy inundation and in and around Chennai city and its suburban areas, and more than 50,000 people had to be evacuated from the existing low-lying areas. In 2015, rainfall of 50 centimeter occurred between 1st and 2nd December. You see, although this is post monsoon, but in Chennai you find that rainfall occurred during December, November, December. Flooding of less catastrophic nature also occurs regularly in low-lying areas of the city and its suburbans. The causative factor of this menace are inadequate drainage of major rivers and other drainage system. So now I shall come to these slides later. This is Chennai, one of the drain is being cleared. Okay, I'll try to come to this screen later. Do I have to stop this sharing? I think I'll stop sharing this one and share the other one. Now, let me try to show you the Chennai flood. This is Mumbai flood. Sorry.
Notice how there's no pre-roll ad? And here's July 26. Even the mention of the date is enough to bring chills.
Is the audio coming?
14 years ago, on 26 July 2005,
Yes, sir.
Mumbai was battered by heavy rainfall, which caused havoc across all areas, claiming many lives and leaving the city paralyzed. It is the day when rains brought the maximum city to a standstill. Large number of people were stranded on the road, lost their homes, and many walked for long distances back home from work that evening. The rains pushed the maximum city to a shutdown, claiming the lives of over 1,000 people and destroying 14,000 homes. The city suffered a loss of Rs 5.5 billion by damaging around 52 local trains, 4,000 taxis, 37,000 auto rickshaws, and 900 pest buses. The rains could have damaged the city financially, but could not defeat the spirit of Mumbaikars. They were seen helping fellow citizens and stray animals. The floods were caused by the 8th heaviest ever recorded 24-hour rainfall figure of 994 mm. Mumbai railways were majorly hit during the 26 July 2005 flood. Local trains came to a halt due to the waterlogging on the track. People took to the railway track as they did not want to be stranded and wanted to get home quickly. Waterlogging led to a dramatic increase in traffic on road, and many low-lying regions of Mumbai were submerged. Various vehicles such as cars, bikes, scooters were submerged during the 26 July 2005 floods in Mumbai. At present, the monsoon rains and the subsequent flooding keep on bringing back the memories of the 2005 floods. Almost every year, the monsoon season brings scenes of distress from all across the city, depicting its struggle with rains. Subscribe to Midday India. Get direct notifications on all our videos by clicking on the bell icon.
Okay, I could show some glimpse of the Mumbai flood. Now we'll see the Chennai flood.
Hundreds of lives lost, thousands rendered homeless. Rain and roadways destroyed, the airport shut, and the crisis is far from over. Even as the city braces to deal with the worst flood situation in decades, one wonders why has Chennai turned into a virtual island? Sure, it has been unprecedented in 100 years. This, the exceptionally strong El Nino, which is an unusual warming of surface waters in the equatorial Pacific Ocean, is to be blamed. Experts believe it could turn out to be the strongest ever recorded. The El Nino, together with a strong upper air divergence and high moisture content at lower levels, has affected the winter monsoon. But reasons for the catastrophic flooding lie beyond. Excessive rains forced authorities to release a massive 30,000 cusecs from the Chimbaram reservoir into the Adyar River over 2 days, causing it to flood its banks and submerge neighborhoods on both sides. Similar flooding triggers were in action in Pundi and Puram reservoirs and the Kuvam River that winds its way through the city. Mindless urban planning of the city over the last 2 decades has made matters worse. Poor urban planning in Chennai has three aspects to it: illegal construction, choking of water exits, and badly planned or unimplemented projects. According to a report submitted by Chennai Metropolitan Development Authority to the Madras High Court, there are over 1.5 lakh illegal structures in the city responsible for the disappearance of over 300 water bodies. Lowlands have been filled and the concept of storm water drains abandoned, the fundamental instrument of flood fighting. Ironically, neighborhoods like Coimbatore that saw extensive storm water drain projects are also underwater. Experts say that most of these projects have been executed without incorporating crucial data on the topography or the flood character of the site. So on the one hand are these badly planned projects, and on the other, those that haven't seen the light of the day, such as the early warning system to understand the runoff pattern of rainwater and laser terrain maps. Now, while Chief Minister J. Jayalalitha said during the earlier phase of heavy rain last month that damage during the monsoon was inevitable, facts suggest that the disaster could have been man-made. खुद को एक्सप्रेस करना makes me shine. इसीलिए I choose the new casting creme gloss.
Mahom Nepal mapangda kay thay.
And see heart somewhere down the
Now, since I will be presenting this Patna flood, just a glimpses of Patna flood of 2019. It is not very old. This is just recent.
ꯑꯩ ꯊꯥꯗꯣꯛꯑ ꯊꯝꯕ ꯑꯩꯅ ꯑꯗꯨꯝ ꯌꯥꯎ ꯂꯩꯕꯒꯅꯦ ꯍꯥꯏꯅ ꯊꯥꯗꯣꯛꯑ ꯊꯝꯃꯒꯅꯤ ꯔꯣꯃꯤꯌꯣꯁꯨ ꯌꯥꯎꯕꯅꯤ ꯍꯦꯛ ꯌꯥꯎꯔꯤꯅꯤ ꯖꯣꯟꯁꯟꯒ ꯌꯥꯎꯔꯤꯁꯨ ꯍꯦꯛꯐꯝ ꯖꯣꯟꯁꯟ
I request the participants to remain silent. You can hear something in the background. Kindly unmute your. Dear participants, kindly unmute your.
ꯃꯥꯏ ꯂꯤꯡ ꯄꯤꯔꯤꯗꯨꯗꯤ ꯁꯦ ꯆꯦꯛ ꯇꯧꯔꯗ ꯌꯥꯎꯗ꯭ꯔꯥ ꯌꯥꯎꯗꯦ ꯌꯥꯎꯅꯤ ꯑꯩ ꯀꯅꯥ ꯈꯪꯅꯤ ꯑꯩꯗꯤ ꯑꯩ ꯃꯊꯪ ꯊꯥꯒꯦꯅ ꯈꯜꯂꯨꯕꯗꯣ ꯑꯗꯨꯝ ꯄꯥꯗꯕꯅꯤꯅ ꯌꯦꯡꯉꯣ.
Unceasing rain. The deluge in Patna is seen to be its worst in 1975. A city is collapsing. It's our top story. and are grounded for 3 days. Help reached them on Monday. His family was among the 26,000 rescued so far in the city. Sushil Modi was not alone. BJP leader Rajiv Pratap Rudy, JDU's Ajay Alok, and Union Minister Ramvilas Paswan all found their houses submerged in water. Right now we are at the Sri Krishna Puri police station, and very difficult to understand that what kind of situation is prevailing here by the waterlogging.
अभी तो बहुत लेवल था, ये तो कम हो गया है, बहुत ज़्यादा लेवल था, पूरा रूम डूब चुका है मेरा, एंड बहुत प्रॉब्लम हो रही है, एंड प्रॉब्लम है पीछे बहुत सारा पानी है और उससे कम नहीं हो रहा है, और ये पूरा
To do. Patna is just a symptom of a bigger ailment, that of India's crumbling urban infrastructure. With Sujit Shah, Rohit Kumar Singh,
Okay, thank you for this watching this some video. Now, is this screen visible to you? Some slide.
No, sir.
Huh?
It's not visible, sir.
This is not visible. Okay, let me try to put it again. Just a moment. Am I audible?
Yes, sir.
Am I audible? Okay, now I think there was some connectivity problem. So now we were in Chennai Flood 2015. This slide we have seen. So now this is the condition of drains. So whole ACM means JCB is in the drain and it is clearing all the debris that has been collected. It consists of all plastics, all types of material here. So drains are being cleared. So you see there is a culvert here, and you see all the debris are almost touching the deck of the culvert. So those are the people, they were cleaning, they were responsible for the cleaning, drains touching the culvert. See, this is the clearance. So if there is rainfall, definitely this is going to spill out. So choked drain inlets, there are places where the rainwater is supposed to go. So, but these are all choked. There are plastic materials in it. So now coming to None. None. I don't have. Hello. No. No. Okay, am I? Hello. Yes, ma'am. Yes. Screen is not sharing. Maybe there is a connectivity problem. Okay. Without PowerPoint. Okay, that is fine. Okay. Huh? One minute. Has it come? Yes.
Yes, sir.
Yes, sir.
Okay. Now I think after a long time, okay, we could share it. Okay, we proceed further. So this is the condition of the drain that I have. I was trying to. So in the recent past, Patna was heavily flooded in the year 1975-76. There was a severe waterlogging in the year 1990, 1997, 2019 in the town. Small boats could be seen on the road. Due to flat topography, storm water does not flow under gravity to river Ganga, or there is another river called Punpun during the period of flood. Pumping is the only means to dispose the rainwater of the town. The causative factors are rapid development of new unplanned colonies and their commercial activities without proper drainage system has aggravated the problem of waterlogging. I showed you the video of Chennai city. There also it was spoken that unplanned development of the colonies. Then a lot of people are coming to the town, and there is indiscriminate. These habitations are growing. Those are the causative factors for the urban flooding. On top of this, there is no proper garbage disposal. All the garbage you will find, most of the garbage you will find on the drains, and that is choking the drains. So objectives was evaluation of the existing stormwater drainage network, efficiency of the study area, computation of inflow and outflow hydrograph at various outlets, and water surface profile along the stormwater drains. Then it also had the objectives of to find out the feasibility of improvement of the existing network of the stormwater drainage and propose additional network to avoid urban flooding, and finally the technology transfer. So, for any if any new city is coming, then we can plan for urban drainage. But for an old city, we cannot just uproot the old system and install a new one, because there are already habitations. So we have to be careful. So methodology, catchment delineation and determination of its characteristics, preparation of thematic maps like stormwater drainage network, land use, soil, percentage slope maps in GIS environment. Then hydrologic analysis of rainfall, estimation of design storm for various return period, analysis of existing cross section of the drains to assess whether the sections are adequate to carry the storm runoff using stormwater management model. Development of water surface profile along the channel and the outflow hydrograph, and the evaluation of the system. So these are the process of storm to sewer network. Rainfall is occurring. It is falling on the catchment. Then through sewers and these conduits, it is coming to an outlet. So as far as the rainfall is concerned and the catchment characteristic is concerned, it is dealt in a hydrological model. And when there is flow from the nodes to the links and finally to the outlet, it is dealt in a hydraulic model. So the tools used are GIS, EPA, SWMM. This is the model we are using. So this is a network of the drainage system found in an urban city. These are buildings. There are parking lots. This water rainfall is occurring, and it is being accumulated from the roads, parking lots, etc. These are from a catchment. These are coming to a nodes, and through a link, these are coming to different points. Sometimes these are also treated. There are weirs, there are pumps. Then finally, there is outfall. So this is called as the subcatchment. Rain is occurring. It is falling on the subcatchments. From the node, it is from the catchment. It is coming to a junction, and from junction through a conduit, it is flowing further. There are weirs. there are orifices, there are storage units, there are dividers, pumps, and finally it is in the outfall. So stormwater management model is a distributed dynamic rainfall runoff simulation model used for single event or long-term or continuous simulation of runoff quantity as well as quality from primarily urban areas. So these are the process model: precipitation, then surface runoff, overland flow, then channel pipes and storage routing. There are treatments. Then ultimately it is in the in the outfall. What are the hydrologic modeling features? It is spatially and time varying rainfall. These are the features. If it's a varying rainfall, it can deal evaporation of standing surface water. This can be dealt. Snow accumulation and melting can be dealt. Interception from depression storage, infiltration into soil layers, percolation into shallow groundwater. This can be dealt. Then interflow between groundwater and channels. Then non-linear routing of overland flow. Hydraulic modeling features. It can handle drainage network of any size. It can accommodate various conduit shapes as well as irregular natural channels. This I will show you. Then model component consists of pumps, regulators, so it allows external inflows from runoff, groundwater, then rainfall derived infiltration or inflow. Then it is from dry weather flow, sanitary flows, and user supply time series input. It uses flexible rule based control for pumps and regulators. Models it can model various flow regimes such as backwaters, surcharging, reverse flow, and surface ponding. So it has got a very wide variety of features to handle. It can deal with groundwater, surface water. It can deal with if there is a reverse flow or backwater effect from the sea, etc. This can be dealt. Then it can also it is also capable to do water quality modeling features like pollutant built up over different land uses, pollutant wash off during runoff events. These all can be dealt in this SWMM model. Typical application: design and sizing of drainage system components, including detention facilities, floodplain mapping of natural channel system, then control of combined sanitary sewers overflows, then generating non-point source pollutant loading for waste load allocation studies, then evaluating best management practices. There are certain limitations. It is not applicable for non-urban watershed. It is not applicable for forested areas or irrigated cropland. Cannot be used with highly aggregated, for example, daily rainfall data. We need very hourly or less than hourly, sub-hourly rainfall data. It is an analysis tool, but not an automated design tool. Now, flow routing algorithm, it uses one-dimensional Chern-Binards equation to solve this problem, to calculate water surface profile as well as the velocity. And here, in this particular exercise, we have used the total Chern-Binards, one-dimensional Chern-Binards equation. And this is the total equation it solves. So, what are the flow routing algorithm? We are using here the dynamic wave routing. It's a non-uniform, unsteady flow, solves continuity and momentum equation for conduits and a volume continuity equation at nodes. Backwaters surcharge, looped or parallel sewers, strict routing of flooded sewer manholes. So this can solve all types of means variabilities. So this is the conveyance system of Patna township. Mostly you will find that drains are not cleared. Had it been cleared, then most of our problems would not have been there. So these are different outfalls. This is pumping house, water level gauge we have installed here for carrying out our study. This is one of the outfall. This is another outfall. So Patna, this is the line diagram of Patna. So it is divided into several zones like Western Zone, East, Central Zone, Southern Zone, and Eastern Zone. The Western Zone, Central. Am I audible, sir? Am I audible?
Yes, sir. Very well, sir.
So it is divided into Western Zone, is Central Zone. Western Zone deals the drains. This means urban water through these conduits, and it is going to some outfall called Kurji outfall. Then another conduit goes to Rajapur outfall, Mandiri outfall, Antaghat outfall, Krishna Ghat outfall. This is going to River Ganga. And there is another river called Punpun. There is an outfall here too, Pahadi outfall. So before carrying out the study, we had to find out what are the length of different drainage network in the town. So it was something like somewhere it is 6 kilometers, somewhere it is 8 kilometers, somewhere it is less. So it is Western Zone, Central Zone, Southern Zone, and what are the name of the drains. So this is enlisted here. So these are the drainage cross sections we could collect from the municipal authorities at different location. So before for conducting this study, first of all we had to know the detailed topography of the area, and mostly you will not find the detailed topography of an area. Survey of India topo sheet, it is 1 in 50,000. Municipal area maps, what we could collect was 1 feet contour interval, and that was also not for the whole of Patna town. So additional spot heights we had to collect. So we could generate the DEM of the study area. Then from the DEM, we could find out the percentage slope of the study area. Then with these two information, we could segment whole Patna into 50 different segments. These are called as sub-catchments. Small areas are segregated. In total, there are 50 such sub-catchments. See, during last 30-40 years, Patna has gone, Patna or for that matter, any urban city has got a lot of changes, lot of built up area has come up, lot of impervious areas have been created. So this is land use classification that we have done. And this land use classification, this will give us an idea of how much porous is how much is the impervious here, what are the different land use in the area, how many water bodies are there, roads, railways, etc., low-lying areas, etc. So this is data preparation for in SWMM model, stormwater management model. As I said that the area has been segregated into 50 sub areas, and these sub areas have been dealt separately. From these sub areas called as subcatchment, water is collected in a junction, and from junction these are carried through a conduit to a particular outfall. So this I will try to show if the means network is okay. I will show the simulation how we have done it. So these are the characteristics of a subcatchment. It contains we name and we give it a codes just for better identification. It has got X coordinate, Y coordinate. Then it is associated with rain. Whether this rain gauge contributes to this subcatchment or not. And if there are many rain gauges, or if there is a rain gauge in this subcatchment, we can take the data from that rain gauge. So there is an outlet here. See, here this has been designated as KRJ JEN1, means it is node. Node means a junction. So it is the name of the outlet is KRJ JEN1. So name and this outlet name, this looks similar, only the last two alphabets differ for better identification. Area is given, what is the width, means perpendicular to the flow length is the width. Then what is the percentage of slope, percentage imperviousness, then what is the roughness coefficient for impervious area. Definitely it will be lesser than the pervious area. Then depression storage for the impervious area, depression for storage for the pervious area. Then percentage of impervious areas is 25%. Then for the infiltration we are using curve number, where we are the input values are curve number, conductivity and the drying time. This is the subcatchment characteristics. Now let us come means from the subcatchment characteristics to the node and link characteristics. This is junction or the node characteristics, like inflows, then whether there is any treatment plant available, then what is the bottom elevation of that junction, then what is the maximum depth, then what is the initial depth. So these are the parameters that we have to insert as the input to the model. Then there are links. Links are these are the cross-sectional areas. These are the conduits. Somewhere it can be elliptical, somewhere it can be rectangular, somewhere it can be trapezoidal or circular or pressurized flow, or for that matter even it can be an irregular shape as it is shown here. So one such this network of drain starting from a point till it comes to an outlet is shown here, and what are the its parameters are given here. See, for this cross section, this elevation at different point starting from the zero, from the left to right is given here. Drain alignment. Then we come to the hydrologic analysis. Rainfall analysis from 1975 till 2005, 2006, 2007. We had the rainfall. This is the yearly means maximum daily rainfall occurred in a particular year. And initially, I said that this daily rainfall is not enough for urban drainage study. So we from daily we picked up the hourly maximum rainfall. Then we did frequency analysis to find out the return period of various means rainfall for different return period. Then we distributed that rainfall. This is daily rainfall. Then we had to distribute it through some mechanism. So this is somewhere it is available. Some coefficients are available. So we just applied this and we found out what is the distribution in 24 hours. So once we have arrived at the this storm for a particular return period, then we have gone to the actual work. For different outfall, means we have run the model, and the model computed the hydrograph, discharge versus time. It has computed the hydrograph, but that hydrograph is for a particular rainfall. So when the rainfall was occurring at the same time, we also went to these outfall and measured the velocity with current meter, etc. With current meter and try to calibrate the model. So for different outfall, for various outfall, For the purpose of calibration, we did that exercise, and ultimately we found that whatever model has computed, this is observed, dotted line is observed, and this is modeled. Modeled means it has solved the Saint-Venant's equation, fully dynamic equation. It has solved. It has solved the Saint-Venant's equation and computed the water surface profile. And we found that model is behaving well because our observation also speaks the same language. This is calibration at Rajapur, this is at Kurji, this is at Mandiri, this is Pahari. So once we were satisfied that at different outfall, the model is behaving well, so we have gone for different prediction. So we found that how much is the error between the observed peak flow and simulated peak flow, and we found out what is the root mean square error, what is the relative error, etc. for different outfall. So once we knew that, then we tried to simulate the model for 2 years, 2 years return period rainfall, and found out what are the hydrograph at different outfall. So somewhere wherever there is a lot of contribution from the catchment, it will have a higher peak than the other one having lesser number of subcatchments. So this is outflow hydrograph at various outlets for 2 years return period rainfall. So here we find that all the drainage system. This is one of the drainage system. This is 7 kilometer. Means you should take mind that this is not in scale, so it is not a direct fall. This is over a length of 2 kilometer. This slope. So what we find here is even the existing drainage system is not able to accommodate even 2 years return period rainfall, because this all drainage system is totally full. Totally full means it is spilling out and causing waterlogging. This is the case not only for this conduit, means one drainage system. The same story is applicable for other drainage system. You see here there will be there will be spilling out. Here there will be this means a drain will be spilling out. This is a Kankarabag drain. See, after some point there is a sump. It pumps water to another leak, and then it flows to the outfall. From here, from here it is going to Pahadi outfall. See, from here there is a slope. From here there is a slope. So it is going to this outfall. Similarly, for another Mandiri drain, you see that it is totally full and it is spilling out. Another drainage network, it cannot accommodate 2 years rainfall. So once we assure that this drainage system, these are spilling out, definitely total inflow. This is total inflow is more than the total outflow. So when the total inflow is more than the total outflow, so this portion, this minus this is going to cause system flooding, which is depicted here. 2 year return period rainfall, inflow and outflow hydrograph. So this is causing surface flooding of this much hectare meter. These are the rainfall and this is surface flooding. So once we put these figures on the map, so these are the surface water logged areas for 2 years return period. So design criteria we have adopted means 50 years return period. It is for the large cities. For small cities, it is in between 2 years to 25 years. and for a larger city, it should be 25 to 50 years return period we should take. So once we knew that this existing drainage system is not able to accommodate the 2 years return period rainfall, we had to modify our drainage cross sections. So we cannot build additional drainage network abruptly, nor we can expand them. So what we can do is modify their cross sections. So this is the existing drainage system. This is the proposed drainage system. Trapezoidal, we have modified to rectangular. Wherever there was irregular, that we have tried to modify. So once we did so, then again we tested our model, and here we could find that it can accommodate 25 years return period rainfall. So here what we find that total inflow, you see the total there is a lag of inflow and outflow. That is obvious. Means total inflow and total outflow is almost matching. Okay, so there is no flooding here. Means area under total inflow and area under total outflow, these are similar. So there is no means flooding in the area. So we could calculate or compute the outfall hydrograph at different outfall, namely at Kurji, Rajapur, Mandiri, Antaghat, and Pahadi, and this has been quantified. So once we did so let us see the what is the effect. You see, you will find here that there is a gap, white color. It is not everywhere. This is cyan color or the green color. It is the maximum water level it has achieved, and it is going to the outfall. See all the drains. It has gone at least some margin. It is not overtopping. So this is another one. This is SK Puri. This is the outfall. So you find that always there is a gap. So this drainage system is behaving well. Another one, it is also behaving well. Then we also see we did not stop for once we had the hourly distribution of rainfall for different return period. We wanted to test it for a severe most storm. So we went to IMD, collected their SRRG chart, and from the SRRG chart, we found out what is the maximum intensity of rainfall occurred in 15 minutes. Because sometimes it may happen that in 1 year it is not uniform rainfall. At some particular duration, there is maximum intensity. So we wanted to capture that, and for that we referred to the individual SRRG chart, and we found out what is the actual rainfall in 15 minutes. Also, we tested our model for 13th August 2007. There was a maximum rainfall that we tested our model. So we found that almost our drainage network is behaving well. So once we did so, then we had to transfer this knowledge to the department. So that's what we did. So this is about the presentation. Now I would like to show you within a short time the simulation, so that you can better appreciate. Now, is it visible? Is the screen visible to everybody?
Yeah, it is visible.
It is visible.
sir.
It is visible.
So, you see, first of all, let me show you. So, this is one of the subcatchment. This is one of the subcatchment, and just a moment. Let me. So means for a subcatchment, you see, these are the different parameters that we have inserted. All these parameters, its area, its width, percentage slope, etc., etc. What is the carbon number? So since we lost much of the time, so I'll try to go a little bit fast. So all the characteristics of the subcatchment has been entered. Likewise, we have entered for entire Patna town consisting of 50 subcatchments. So this is subcatchment. Then let us come to the nodal properties. This is called as junction. So junction parameters have been entered. Then link parameters have been entered. It is trapezoidal. You can so this is trapezoidal, having maximum depth, bottom width, etc. Everything is given. Somewhere it is not so. Like I showed you, this is irregular. So this is like this. So many types of means cross sections are there. So these are different types of cross section that is in Patna town. Now let me link so that it is easily visible. Also, let me try to nodes. So these are different nodes, links. So I will try to explain you. So all the data have been fed to the model. So once the data is fed to the model, it has to be simulated. So it is doing its simulation. It will take only a minute, less than a minute, because data entered are simple in nature. We have not given the distributed rainfall. So we have run the model. Now let us try to see some of the let us try to see what happens to these drainage network or other drainage network. Okay, so let us start with this. This is first junction. This is the start node, and it is going to this outfall. So it is going to this outfall. This is starting node, and this is the end node. And in between there are subcatchments, which is draining to these nodes. So these are the different links. This is called link. Okay, link going to the outfall. So once we say yes, so it is showing me the profile, longitudinal profile. So now let me try to simulate this 24 hours rainfall having a return period of 2 years. See, now it is computing. It will you will see that water level is built up. Is it visible? Are you able to see this simulation?
Yes, sir. It is visible.
Okay, fine.
Yes, it is visible.
This is interesting. Will you mind if I overshoot time by few minutes? Although I am going a little bit quickly. See, you will find that after 12 hours, 12 hour was the peak rainfall. I'll show you. See, here there is a timer. It is 9 hours. It has gone. Uh, at 12th hour, there was maximum rainfall. You will find that whenever there is 12th hour, it will completely fill the drainage system. It will spill out. See, it is spilling out. So it is spilling out, but at the same time, after sometimes, it is coming back. Drainage system is being cleared. Similarly, I'll show for one more. So this is coming down. This is for a particular rainfall. So now let us see rain gauge time series rain 1. So this is the rainfall that at 12th hour there is maximum rainfall. Everything you can see on the monitor. Now let me show you another one. This is the outfall is in Ganga. Here it will be in Punpun. So now let me try to show you another one here. And you try to remember here we have extended in the modified section. This in Kankarwag area it keeps water. It remains waterlogged for longer duration. So we have extended the drainage system here. So this one is the starting node, and this is the outfall. So and in between there are these links. So this is the means L section. See here, the drainage network is coming from here as well as from this direction. So you are finding that I think it is in one direction. This one is going to Punpun River. From here as well as there are two drainage system. So now again let us try to compute the water level. So it is computing water level, and let us try to see what happens in 12th hour. There is a clock here. This is the outfall. Pahadi outfall. There is a pump, Kankarabag PUMP pump. So water is being collected from here, then it is pumped to another network, and then it is going to the outfall. See, there is spilling. Here also there is spilling. So the present system is not adequate to drain out the water even for two years return period rainfall. So now let us modify these links, and then let us try to see. So let us open save, no saving, then Patna modified. Let us try node. See, I have highlighted the nodes as well as the links. So this is the situation where we have modified the network. Somewhere here, I think I showed you the conduit. Now let us try to see. This one is irregular view. See, earlier it used to be something like this, having a less conveyance capacity. Now we have tried to extend its increase its conveyance capacity by modifying the existing drainage network. Likewise, we did for most of the drains. This one I showed you. So now let us see how this system behaves. So before we see, we have to simulate the whatever input data is there. We have to simulate. So simulation is now going on. So simulation is successful. Now let us see how the drainage system behaves for the same drainage network. For the same drainage network, this is starting node. So this one is end node and okay, find path. Okay, so this is the profile. So now let us try to simulate it. And now let us see, it should not, I repeat, it should not spill out. That is what is our intention. See, it is building up, and it will reach its peak 12 hours, and maybe it will last more than 12 hours, and then it will come down. See, it will not spill out. See, it is coming down. Now let us see other things. See, once the drainage system has started from here, it will have lesser contribution. Then once these two becomes combined. Finally, when it is many subcatchments are contributing, then we should get, in this conduit, we should get the maximum discharge. Now let us try to see whether this actually happens or not. So let us start from here. Then not the node but the links. Okay. So this is the link. This is the another link. This is the third link. See, subscript is 1, 2, 3. So there are 5 links. So now let us try to see. See, at the link 5 we expect maximum. At link 5 we expect maximum discharge. In fact, it is showing so. So you see, model is very rational in predicting the outfall hydrograph. Now let us see another thing. We can also verify whether suppose whether this link 5, okay, this is the hydrograph for link 5. Now let us try to see the system. In the system, let us see the total inflow and total outflow. See, inflow and outflow are almost matching, so there is no water logging. Earlier, you see here, I pointed out that we have extended. Earlier, the drainage network was starting from here. So, since it was causing problem, now let us see whether it is causing problem or not. But we have to go to the other one. Here we have extended the network. See, earlier it was this was the outfall and it was up to here, but it was causing problems, so we have extended it to up to here. So now let us see this link. Starting node is this one, ending node is this one. And we find that it will not spill. We can see here. Here 8. This link 1 kilometer we have extended so as to accommodate, because it was otherwise it was spilling out. It is 10 hour, 11th hour, 12th hour it will go to maximum. So let us go out of this exercise. I'll show you one of the output here. This is when the system was not behaving well, it was spilling out. I forgot to show you one of the simulation result. Now you have seen that the inflow and outflow are matching. Here the inflow and outflow will not match. Okay. So here now let us see the system. System says that total inflow and total outflow, let us try to see first. See, total inflow is more, total outflow is less, so there is flooding. Now let us see how much is the flooding. See, this much is flooding. So what we have got, let me now close this one. Okay. Now what we have got, see on the screen, without going to the site, we are able to know how a system drainage network behaves. Are you able to hear me now?
Yes, sir.
Excuse
Yes,
me.
here.
Okay, so without going to the site, you can try different options how the drainage network behaves. You can modify the cross section. You can see different option if you apply this stormwater management model. So once you have the right data with you, so the model works wonder, and we have tried to see its output in Patna. The concerned department, they have taken our output, and in some of the drains you will find that whatever modification or we have suggested, that is actually in place. So you can say that our study was a success story. We have also done similar study for a small subcatchment in Chennai city. But the problem in taking up such a project is you do not have, number one, the detailed topography of the area. Means if even if you have a 20-meter by 20-meter plot, you like to know that from where to where the water will go, or where the outlet is. So that thing will be possible only if you have a detailed survey available with you. So uh, So this is an excellent tool, not only for the executing department, even for the decision maker. Let me clarify you one thing here. Whatsoever analysis I have shown you, this is without debris or we have assumed that the drains are clear. In actual situation, this is never so, and in the model we can put these practical field situation in place, and we can simulate the model. So this is all, everything is possible. Now, okay, we have overshoot our time, and now I would ask participants, although the time has shot up, and in between we have lost quite some time, 15, probably 10-15 minutes. Since there was a network problem, this happens with virtual training. So yesterday also my colleague Dr. Mani, he had to deliver his presentation from his residence, because in our office that there is network problem of BSNL. So he did it from there. Today also I am doing from my residence. It generally does not happen. It has got 100 Mbps, but sometimes it happens. We have to accept the truth. So with this, I thank you for your patient hearing. Now, if you have got any comment or anything, then I would like to, I would be pleased to answer them. Or maybe I have given my email address. If you need any further information, we are always accessible. Or you can contact Madam Victoria if you need. I'll pass on my presentation to her. So with this word, I thank all the participants, and sorry, I have kept you waiting. You are getting delayed for your lunch, but nonetheless, let us accept that, okay, these are wonderful tools. These are available with us, but the problem is we must have proper data with us. Yes, this network design is possible. So, Madam Victoria.
Any questions from the participants? If we do not have any questions, I would like to request Hazarika sir to say a few words. I request someone has put on the someone has I request some of the participants unmute it. Unmute the this thing, Talia, unmute it. I request Hazarika sir to say a few words.
I think there is one question. Which simulation software you are using for this model? It is stormwater management model, and it is it is available in public domain. So we did not spend any money to buy the software. It is available in public domain, and this is a wonderful software that we have found.
Thank you, sir, for your detailed presentation. So, sir has covered today this case studies of flood management, the river bank erosion control, and the model studies you have shown in detail. Also, sir highlighted about detail about this urban flood. That shown the videos of the urban flood in Mumbai, Chennai, and also Patna, and some approaches like how to mitigate such urban flood, like cleaning of drains, etc. So that detailed methodology also shown that the hydrograph techniques and also the detailed criteria of flood control structures, the model simulation, etc., which will be very useful in mitigating and management of urban flood and also the river management. As these are increasing in the urban cities nowadays, we also experience in our place in Northeast this urban flood situation in Guwahati, Imphal, and these cities. Of course, it is less in hilly areas because of good drainage. But increasing in small cities also because of various reasons like drainage congestion and increase of runoff due to different reasons. So, but this scientific approach and scientific techniques are always necessary because to mitigate such increasing problems. So, we are very much thankful to you, sir. And both these days, today and also yesterday, two renowned scientists in the field of this flood management and erosion control covered this topic elaborately with detailed methodology and scientific details, which will be very useful for the implementing agencies, also academicians, researchers, and which in huge participants shows their interest. Many of them and also observed and watched, attended through the YouTube link, and this will be available both in the YouTube channel of Neriwalam. And these presentations, the presentation made by Dr. Pankaj Moni on the first day and Chakravorty sir in the second day will be made available to the participants. So with these remarks, we would like to conclude for today and also to the sessions. So now I would like to hand over the session to Dr. Bhia, our training coordinator.
A very thank you to the Sri B. Chakravorty sir and Dr. U.M. Hazarika, who had taken all the pains for delivering or for arranging these training programs. I'm thankful to all the participants for their continuous support and their comments. Good comments are coming, still coming, sir. But they all are very happy to get such informative sessions in the last 2 days. And this is just a trial and just an introductory, sir. We are also planning for once the COVID situation is improved, we are also trying for 5 days program, so that all the people are trained either in the software or in other ways to manage the flood. So their participants, whenever we give any message regarding offline training, please do come to Neriwalam or NIS, wherever there is a convenient place. We'll be again doing it in the next financial year, collaborating with different institutes. So this is just an introductory about the informations that we all have within us, and we also want to share with all of you. So thank you, sir, for your nice presentation, and thank you all to all the participants for attending this 2 days online training program on flood management and erosion control. And I hope this brings some knowledge and skill while tackling the flood problems and erosion controls in your place. Thank you all.
Thank you, everyone.